Welcome to the deep dive. We're skipping the intros today and jumping straight into some pretty advanced stuff in data science theory. The goal here is to get beyond just the definitions you see everywhere and really dig into the core ideas.
Yeah, we're going to look at some fundamental model types, maybe bust a few myths about how deep learning optimization actually works, and talk about the engineering needed to keep these huge models stable.
Okay, so let's kick things off right at the foundation. This split between generative and discriminative models, it sounds like it's all about probability.
Exactly. It boils down to what part of the probability puzzle they're trying to solve. So a generative model, it's ambitious. It learns the whole thing, the joint distribution PXY.
Meaning it learns how the data features X and the labels Y occur together.
Precisely. And because it understands that relationship, it can actually generate new data points. Think like Janins creating images or VAEs. It's building a model of the world, essentially.
Okay, so world builders versus, what's a discriminative approach then?
Discriminative models are much more focused. They only care about PYX.
The probability of the label given the input.
Right. All it needs to know is, okay, I see this input X, what's the chance it's labeled Y? It's purely about distinguishing between classes, not generating them. Think your standard deep classifiers.
And this choice, it affects the kind of loss function you'd use. Like cross-entropy gives you actual probabilities.
Yeah, cross-entropy loss aims to give you calibrated probabilities outputs that actually reflect the true likelihood, PYX. But then you have things like max margin loss, like in SVMs.
Right, Mahun's loss.
Exactly. That one doesn't really care about probabilities being perfectly calibrated. It's all about pushing that decision boundary as wide as possible, maximizing the margin.
So it's sacrificing maybe some statistical nuance for just raw classification robustness.
You could put it that way. It's solving a slightly different problem, boundary maximization, not probability estimation. Both useful, just different goals.
Okay, that distinction makes sense. But when we actually try to train these deep models, things get messy. Yeah. Which brings us to maybe the biggest myth when I'm training a model.
Think of the loss function as this incredibly bumpy, complex terrain you're trying to find the lowest point in. Without batch norm, it's full of sharp cliffs and really unpredictable slopes. You have to take tiny, careful steps, a small learning rate.
Okay.
Batch norm essentially sands down those cliffs. It improves the mathematical properties like Lipschitzness and gradient smoothness. This lets you take much bigger, more confident steps.
Ah, so you can crank up the learning rate without the training exploding.
Exactly. And that drastically speeds up convergence. It's about enabling faster training by making the loss surface easier to navigate, not primarily about fixing shifting distributions mid-network.
Fascinating. So we engineer stability there, but then there's this other thing that seems to break all the rules.
Yeah.
Double descent.
Right. This one's really counterintuitive from a classical stats perspective.
Yeah, the idea that test error goes down, then up as the model gets complex enough to fit the data, but then it goes down again when it gets massively over-parameterized.
That's the one. It peaks right at that interpolation threshold where the model just fits the training data perfectly. And then, yeah, performance gets better again as you add way more parameters than you seemingly need.
Why does that happen? It feels like massive overfitting should just keep getting worse.
It's a super active area of research. But the leading idea is that in this highly overparameterized regime, the optimization algorithms we use, like SGD, have an implicit bias. They tend to find flatter minima in that vast loss landscape.
Flatter minima, meaning solutions that are less sensitive to small changes in the input.
Sort of, yeah. These flatter solutions tend to generalize better, even though the model has enough capacity to memorize every single training point, including noise. So using huge models isn't just okay, it might actually be beneficial because optimization finds better generalizing solutions within them.
Wow, okay. That explains a lot about why people use such enormous models.
Yeah.
Let's shift gears slightly to deliberate engineering for stability. The transformer architecture is a great example, right? Specifically that scaled dot product attention.
Absolutely. That little scaling factor, dividing by the square root of dk, the key dimension, that's crucial.
What problem is it solving? Why divide by that specific value?
It's all about controlling variance. When you compute dot products between high-dimensional vectors like the query Q and key vectors in attention,
which can be hundreds or thousands of dimensions long.
Right. The variance of that dot product scales linearly with the dimension, dkp. If you don't control that, the dot products can become huge.
And if those values going into the softmax function are huge,
Softmax saturates. It outputs values very close to 0 or 1, and the gradients become tiny, almost 0.
which means the model stops learning effectively, vanishing gradients.
Precisely. So that division by the square root of dk is specifically designed to normalize the variance of the dot product back down to 1, regardless of the dimension.
It keeps the inputs to the softmax in a sensible range where gradients can actually flow.
Exactly. It's a calculated move, pure variance control, to ensure stable training for these deep attention mechanisms. It's essential engineering. Looking back at batch norm, double descent, finding flat minima, and this attention scaling. There's a common thread, isn't there? It's all about deliberately managing or benefiting from the scale and variance of activations and gradients to make optimization work.
Yeah, stability seems to be the name of the game, often achieved through these clever, sometimes counterintuitive mathematical tricks or implicit biases. So, building on that idea of stability and how models learn, here's a final thought for you to chew on. Think about catastrophic forgetting. That's when a model trained on one task completely forgets how to do it after you train it sequentially on a second task. It highlights how fragile that learned knowledge can be. Maybe look into some of the ways people try to fight this, things like elastic weight consolidation, progressive neural networks, or even replay techniques. How do we build models that learn and retain? That's a huge ongoing challenge.